I want to compliment the organizers for putting together such an interesting symposium and inviting me to speak. Thank you. I think it's, in view of the declining support and activity in the area of Fischer-Tropsch, unfortunately, that it's a good time for us to assess where we've been and what we've learned. And I've been doing that this last year, having written a chapter on recent technological developments in FT technology, which will appear in a book edited by our session chairman, Laszlo Gucci, entitled New Advances, Recent Trends in CO activation. It's, of course, impossible in a period of 20 minutes for me to discuss all the details that appear in this chapter involving some 250 references, papers, and patents. And so, rather, I will hit the high points, discuss some of the principles, and talk a little bit about principles of catalyst design. So if we could have the lights down just a little bit and have the first slide. Let's see, I've got to find out which way to turn that. There we go. Now, in my talk today, I will focus on new catalyst developments, and I will skip the part on new developments in reactor process design, since that will be covered pretty well in the next session. The focus of my talk will be on catalyst and process developments which have occurred in the past decade, and we'll look at three important areas of FT catalysis: chemical modifications, including additives, promoters, supports, pretreatments, preparation methods, and the use of zeolites involving interception of intermediates, dual functionalism, and secondary reactions. And we'll examine this question of whether there is, in fact, limitations on chain growth by shape selectivity in Fischer-Tropsch synthesis. The fundamental principles of catalyst design will be emphasized. Now, there are a number of limitations, have been a number of limitations historically in the Fischer-Tropsch process, and they include, foremost, the limited selectivity for premium products such as olefins, gasoline, and diesel fuel. But also, as mentioned in the previous talk, problems with catalyst deactivation, high capital costs, of course heat removal, and less than optimum efficiency. Fortunately, in the past couple of decades, there have been some improvements in technology, which include a significant progress towards the solution of deactivation, heat removal, and thermal efficiency problems. Progress, especially in understanding relationships of catalyst structure to activity and selectivity properties, which provide now a scientific basis for catalyst design. And key recent improvements in catalyst reactor and process technology, which together enable improvements in process economics of 30 to 40%. Now, one of the major limitations I mentioned was the selectivity problem. Selectivity in Fischer-Tropsch synthesis is governed by the Anderson-Schultz fluorokinetics because this is a polymerization process. And this shows the product distributions predicted by Anderson-Schultz fluorokinetics as a function of the degree of polymerization. The first point is that no one product other than methane can be produced at 100% selectivity. And most of the other products only at poor selectivity. For example, on the next slide, C2s at a maximum selectivity of 30%, gasoline and diesel fuel 48 and 41%. 70%, however, for the waxes. Fortunately, now there are some fundamental design principles that can can be used to operate within these constraints of Anderson-Schultz-Flory to get at the desired products. First of these principles is that the rates of production of hydrocarbons and product selectivity in Fischer-Tropsch synthesis can be controlled in large part by careful choices of, first, catalyst properties, second, process conditions such as temperature, pressure, reactant concentrations, and third, reactor design, and fourth, process design. The second principle is that there are some fundamental chemical levers that can be used to affect selectivity, and they are chemical modifications of the catalyst. The ones that we're going to be talking about are additives, promoters, supports, and pretreatments, and preparation methods. And second, interception of the intermediates using zeolites. Let's highlight now a few examples of recent developments in catalyst design. These are more principles. Now, if we're going to discuss the activity and selectivity of Fischer-Tropsch catalysts, we need to start with a baseline comparison of the catalysts without additives and promoters. And so I've listed here the activities and selectivities for representative unpromoted cobalt, iron, and ruthenium catalysts at 480 degrees Kelvin, hydrogen to CO ratio of 2 to 1 atmosphere. These catalysts were at low dispersion to avoid effects of metal. The results were obtained at low conversions to avoid effects of heat and mass transfer, and these data were obtained at BYU and Berkeley. The first thing I'd like you to notice is that the cobalt alumina catalyst is about a factor of 10 more active than the ruthenium and iron catalysts. It also has the highest propagation probability of 0.9, and it is substantially higher than the values of around 0.7 for ruthenium, which are much larger than the ones for the unsupported, unpromoted iron. Note too that the iron is the best, the most selective for olefins, and of course the cobalt is least selective. Now these are the baseline properties, but we're not stuck with these properties because we can use all of these modifiers that we talked about to change the activity and selectivity. For example, we can use potassium to change the selectivity for olefins, and these data from Arakawa and Bell show the changes in activity and selectivity as a function of potassium-iron ratio. For example, the total conversion of CO and production of CO2 go through a maximum. The production of alkanes drops off significantly, while the production of olefins or alkenes remains roughly constant with increasing potassium to iron ratio. Now what that means then is that there is a very significant increase in the olefin to paraffin ratio as we add potassium. Now for an example of the effects of catalytic properties, I wonder if we could get somebody to focus that for me, because I don't want to try to turn this thing off. Thanks. Now this is some studies of cobalt on alumina conducted in our laboratory, and what we're looking at are a set of cobalt alumina catalysts prepared by impregnation. And what we see here is the effects on catalytic and physical properties. Let me just lead you through this. These are catalysts ranging in metal loading from 3 to 25%, and as we increase loading in this range, we see a big increase in hydrogen uptake, and in the percent reduction to the metal, a decrease in dispersion from about 15 to 5%. At the same time, there is a very substantial increase in the turnover frequency for CO conversion and an increase in the activation energy and pre-exponential factor. Well, these are significant changes, but let me further state that we have found that the activity of cobalt can vary over 4 orders of magnitude depending upon the preparation, support, and metal loading and dispersion. And furthermore, in the next slide, we show data from a study by Rule in our laboratory indicating that the selectivity is also a function of dispersion and metal loading. And these are data for a half a dozen catalysts on different support. Actually several different catalyst systems and at loadings of 3 and 10 weight percent. And notice that the average carbon number here varies from about 1.5 or 2 up to 7 as we decrease the dispersion by about a factor of 10. So there are enormous changes in the activity and selectivity of cobalt as we vary the physical properties. Now, are these a result of changes in the surface structure, or could they be due to metal support interactions or promoter effects? In a recent study by Johnson and co-workers in our laboratory in collaboration with Wayne Goodman, we found that as we varied dispersion over the entire range from 0 to 20% for highly reduced cobalt catalysts, that there was no variation in the CO turnover frequency. In other words, the specific activity is independent of dispersion in cobalt catalysts that are well reduced. There is a deviation of these catalysts here of low loading and which were poorly reduced, and in fact on the next slide we find that if we plot the turnover frequency as a function of the percent reduction, we see that there's an increase in activity with increasing extent of reduction. In other words, the activity correlates better with extent of reduction, or seems to be more related to support effects or maybe effects of unreduced metal oxides rather than an effect of surface structure. Now, let's look at the effects of support. And this shows this study of Rankin in our laboratory shows the effects on activity and selectivity of changing support of iron. For example, the carbon monoxide turnover frequency decreases in the order iron, iron carbon, iron silica, iron alumina. The olefin paraffin ratio is about a factor of 10 higher for the iron carbon. Now, all of these catalysts are poorly reduced, and so we would not expect that this could be a direct metal support interaction. So could it be something like a decoration effect in which the support is acting as a promoter? This is also a study that was done in our laboratory on on the activity and selectivity of nickel in methanation. And what we see here are the turnover frequencies for a set of catalysts prepared by 2 different techniques, impregnation and precipitation. And I'd like you to notice that regardless of preparation, the nickel silica catalysts are about as active and selective as nickel for methanation. So they're very they're very active catalysts, but highly selective for methane. And I should mention the total bar length here corresponds to the methane turnover frequency. The CO turnover frequency. The shaded part is methane, and the unshaded part are the C2+ hydrocarbons. And what we see is that in precipitated nickel alumina and nickel titania, we have an order of magnitude higher activity, and we get very high selectivity for the C2+ hydrocarbons as well as methane. In other words, what I'm saying is that by making changes in the preparation or technique or using promoters, it's possible to take a methanation catalyst and make it into a Fischer-Tropsch catalyst. Now let's talk a little bit about zeolites. I have some data here from Rao and co-workers at PETSI, and they looked at the selectivities of iron ZSM5 and iron silicalite. These were relatively poorly reduced iron catalysts, fairly high loadings on these zeolites. I'd like you to notice the more acidic, the iron on the more acidic support, the iron on ZSM5, produces quite a bit of aromatics, a large fraction, and a high quality, high octane gasoline. On the other hand, the iron silicalite of much lower acidity gives us mainly olefins, or a highly olefinic product. And so here we see the role of acidity in affecting secondary reactions, because it doesn't seem reasonable that in these poorly dispersed catalysts where the iron is not inside the zeolite cage that we would be getting shape selectivity. Well, that brings up the question of shape selectivity. Is it important in CO hydrogenation? In a recent study by Michael Baird, he looked at cobalt, which was very well dispersed and inside sodium Y zeolite, and found that if you ran the catalyst for only 6 or 26 hours, you did get a cutoff in the Anderson-Schultz-Flory distribution at around a carbon number of 9. If, however, you ran it for 47 hours, you got the regular straight line Anderson-Schultz-Flory distribution, rather than what other people had reported as a cutoff after only running for 26 hours. Of course, we know that we get that Anderson-Schultz-Flory behavior in cobalt-kieselguhr, but Baird showed that by physically mixing cobalt-kieselguhr and sodium Y zeolite, he could mimic the shape selective effect if he only ran for 1 or 25 hours. In other words, what I'm saying is most of or in fact all of the previous studies that I'm aware of in which people reported cutoffs in the product distribution were probably due to artifacts, because they simply didn't wait long enough for the higher molecular weight products to fill the pores of the zeolite and come to steady state. Well, what accounts then for the remarkable, unique selectivities that we observe on zeolite-supported metals? In some careful studies by Goodwin and co-workers, it has been shown that these are a result of the different acid functions in the zeolite, secondary reactions that occur on the zeolite, such as isomerization, oligomerization, or hydrocracking. Well, based on the examples which I've highlighted, and quite a number of other important studies that have been done in the last decade or so, I've listed 4 or 5 principles, well, let's say a half a dozen principles that are involved in catalyst design for Fischer-Tropsch. First, hydrocarbon selectivity in steady-state Fischer-Tropsch. Synthesis is generally governed by the Anderson-Schultz-Flory polymerization kinetics, which limit the production of olefins, gasoline, or diesel to less than 40 to 56%. However, it's possible to obtain 70% waxes by operating at a polymerization probability of 0.95. However, attempts to circumvent ASF statistics by means of promoters, interacting supports, high metal dispersions, and shape selective supports have generally met with failure. Second, it's possible to achieve a maximum yield of a given hydrocarbon product within the constraints of ASF kinetics, that is nearly 100% olefins, C2, C4 olefins, for example, and a large fraction of branch products, by one, careful design of the catalyst through the use of promoter supports, gaseous additives, interstitial compounds, or bimetallics, and 2, careful choice of reaction conditions. And then I'd like to point out that additives such as promoter supports, interstitial additives, and alloying metals are thought to change the chemistry of the reaction by changing the localized chemical and electronic structure of the active metals. Third, it's possible to circumvent the ASF predicted carbon yields through the use of zeolites and other promoted supports, which intercept reaction intermediates and convert them via secondary reactions such as hydrocracking, isomerization, and oligomerization to lighter, branched, heavier, saturated products. Now, it is also possible to cut off the Anderson-Schultz fluoride distribution for a short period of time by selective adsorption in the pores of the support, if you want to do transient operation. And also you can sharpen up the ASF distribution by introducing olefins. 4, the variations in pretreatment preparation and reaction conditions enable almost infinite variations in the composition and structure of group 8 metal catalysts. For example, you can make almost an infinite variety of iron oxycarbides. And all of these will have unique structural properties when fixed by a unique choice of these preparation operational variables determine in turn the catalyst's unique activity and selectivity properties. 5, while metal loading, extent of reduction of the metal, extent of carbiding in the case of iron, and coverage of the surface with promoter or support species affect activity and selectivity in FTS, there is strong evidence that CO hydrogenation on group 8 metals is probably structure insensitive. I agree with Professor Sommerjai on that issue. 6, in bifunctional metal zeolite Fischer-Tropsch catalysis, there are trends of increasing methane and isobutane selectivities and decreasing olefin-paraffin ratio with increasing zeolite acidity as a result of increasing activity for these secondary reactions. Well, we've talked about some principles. Let me just throw out a few examples of new catalyst technology which I picked up on in the patent literature. And I know there's a number of people like Rocco who have participated in these developments, the people from Shell that I'm sure are here. They include, for example, an iron manganese Syria catalyst for highly selective production of olefins and low methane make. Cobalt and ruthenium catalyst promoted with the zirconia, titania, chromia for production of waxes, which in turn can be cracked to diesel fuel and olefins. A cobalt titania catalyst promoted with lanthanides, having improved thermal stability towards regeneration. A cobalt ruthenium titanium catalyst, which can be regenerated in situ, both having high activities and selectivities for premium transportation fuels. High activity in olefin selective iron oxycarbide catalysts. Cobalt borides of high activity and high sulfur resistance. More sophisticated preparation techniques involving non-aqueous solvents or the decomposition of metal carbonyls to produce highly dispersed, highly reduced, contaminant-free supported metals. Bifunctional or mixed metal zeolite catalysts, which due to interception of intermediates produce aromatics and gasoline in higher yields than by Anderson-Schultz fluoride theory. Well, I've summarized in this slide some of the recent technology options that are available to us now for producing some of the premium products that we'd like to produce. And I've listed here catalyst reactors and processes that can be used to produce olefins, gasoline, diesel fuel, and waxes. And I don't have time to discuss these, but I just wanted you to see the broad menu of catalysts and reactors and processes that are available now to us to produce almost any product that we desire. Well, let me wind up now. In summary, the significant progress has been made in the last decade in both understanding of the chemistry and its application to the development of more efficient catalyst reactor and process technologies. The rates of production of hydrocarbons and product selectivity in Fischer-Tropsch synthesis can be controlled in a large degree by careful choices of catalyst properties and, of course, process conditions, reactor design, and process design. Third, the fundamental chemical levers, we reviewed those to select, that affect selectivity are chemical modifications in the catalyst by additives, promoter supports, pretreatments, and preparation methods, and the use of zeolites to intercept and perform secondary reactions. 4, Fischer-Tropsch technology suffers from limitations in regard to product selectivity, high capital cost heat removal, thermal efficiency, and catalyst deactivation. The extent to which a given FT process is affected by these limitations depends on catalyst, reactor, and process design, the combination of those three. Although FT synthesis cannot achieve in one step greater than 40 to 50% selectivity for most of the premium products, it is now possible through a combination of 2 or 3 reaction separation stages to achieve selectivities on the order of 70 to 90% of whatever you like, olefins, gasoline, or diesel fuel. Well, there were a number of recommendations that I had in my paper for future catalyst, reactor, and process developments. I think that because my time's up, I will skip those, and if any of you are interested in reading those, just send me a note.